Welcome viewers, in this video we will see the sinusoidal response of RL circuit. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we will see the topic RL circuit sine response. If the sinusoidal is applied, what is the response of the RL circuit? Resistance and inductance. Consider a circuit consists of resistor and inductance as shown in the diagram. Now we will refer the diagram. So the sine wave is applied. Em sine omega t is the applied voltage. This is the transient current I. Switch is available. R and L is connected in series, resistor and inductor. The switch S is closed at t equal to 0. At t equal to 0, a sinusoidal voltage V cos omega t plus theta or Em sin omega t is applied to the series RL circuit, where V is the amplitude of voltage, amplitude of the wave, and theta is the phase angle. So R and L is connected in series. The switch is closed at t equal to 0. The sine wave Em sin omega t is applied to the circuit. So by using the Kirchhoff's voltage law, we can write the equation. We know that Kirchhoff's voltage law, the voltage rise equal to voltage drop. So this applied voltage is the voltage rise, Em sin omega t. That is equal to drop across resistor and inductor. That is I into R, L di by dt. So the voltage drop across these two is equal to applied voltage. So that R into I drop across in resistor plus L di by dt equal to Em sin omega t. So this is the Kirchhoff's voltage law. Applied voltage equal to drop across resistor and inductor. So here we are going to see the sinusoidal response. So we need to take the Laplace transform. Finally we need to take inverse Laplace so that we can able to find the response of the circuit. So take the Laplace transform on both the sides. Right. So while taking Laplace R into I, R is constant, I is converted into I of S. This is T domain, now converted into S domain. Similarly, L into S I of S. Laplace transform of di by dt is S into I of S into Em. Em is constant. Sin omega t. Laplace transform of sin omega t is omega divided by S square plus omega square. Now Laplace transform is taken on both the sides. Take this I of S outside, commonly available. So it is R plus Ls equal to Em omega divided by sin square plus omega square. Bring this term in the denominator, that side. So that I of S equal to Em omega divided by S square plus omega square into 1 divided by R plus Ls. Right. Now we can go for the further simplification. You take this L outside. Now we are going to take the inverse Laplace. In that what we need is S plus, the standard form. Here S square plus omega square is available. Similarly here we need S is needed. S plus A, S plus B, like that. But here L is available, so L is taken outside. While taking L outside, it is R by L plus S. S into L, L is taken outside, but here L is not available, so divided. R by L plus S. So we can write it as I of S equal to Em omega divided by L. This is Em omega divided by L divided by S square plus omega square one term. S plus R by L is one term. We can take the inverse Laplace, but it is in the standard form. It should be in standard form. Then only we can take the inverse Laplace. We can take the inverse Laplace of this term alone and this term alone. We cannot take for both. So that we can use the partial fraction of this I of S. After taking partial fraction, we can easily take the inverse Laplace. Right. Now we'll see the how to take the partial fraction technique. So this is the term available. Em omega by L S square plus omega square into S plus R by L. Some standard procedure available. Accordingly it is split as K1 divided by S plus RL plus K2S plus K3 divided by S square plus omega square. Here S square there means the two terms will be there. K2S plus K3. Only S means only one term. There are 3 or 4 types available. Is coming under the third type, having S square. Right. Now see this, it is splitted into two terms. By finding the value of k1, k2 and k3, we can easily take the inverse Laplace of these two terms. This term is now converted into standard form so that we can easily take the inverse Laplace. But we need to find the value of k1, k2 and k3. Now this side the LCM is taken. We take the LCM. So here only s plus r by l is available. This term is not available. So it is multiplied. Here s square plus omega square available. This term not available. So it is multiplied. Right. So this term is multiplied here. This term is multiplied here in order to take the LCM. Right. After taking that, these two terms available on both the sides. So this is cancelled. These two terms cancel and these two terms are cancelled. We'll see after the cancellation, we'll go for the further simplification. So after cancelling these two terms, now become Em omega by L equal to K1 into S square plus omega square plus K2S plus K3 multiplied by S plus R by L. Now this is the, we'll take this equation number 1 by A. Next step, we need to find the value of K1, K2 and K3. So by substituting the value of S equal to minus R by L. See here plus R by L is there. If we substitute S equal to minus R by L, this term got cancelled. Becomes 0. So that we can easily calculate K1. So we need to identify the S value such that it is become 0. Right. So S is minus R by L means this term becomes 0. Then so that we can find K1. K2 and K3 we can find from the coefficient by equating the coefficient. Right, because here K2 and K3 both are available. So it is better to go for coefficient. So first we will substitute S equal to minus R by L. Em omega divided by L equal to K1 plus S square. So the minus become plus R square by L square plus omega square plus K2 into S is minus R by L plus K3 minus R by L plus R by L. S is minus R. Now this term become 0. Right. So what we have Em omega by L equal to K1 R square plus L square plus R square by L square plus omega square. This term is 0. Right. Now we can bring this term in the denominator. So that Em omega by L into 1 divided by R square by L square plus omega square equal to K1. Right. Now we'll go for the further simplification. So K1 equal to Em omega by L 1 divided by R square plus omega square plus L square by L square. We take this L square LCM. This LCM is taken. Here L square is available, so only R square. Here L square is not available, it is multiplied. Omega square plus L square. Right. Now this L square will go to the numerator. Em omega by L, L square divided by R square plus omega square L square. This L square one term got cancelled. So Em omega L divided by R square plus omega square into L square. So this is the K1 value. So by substituting S equal to minus R by L, we got the value of K1. Right. Some more clarification is there, simplification is there. In frequency domain, the magnitude of impedance RL circuit, impedance of RL circuit is given as Z equal to square root of R square plus omega square into L square. You square on both the sides so that Z square equal to R square plus omega square L square. Right. So that this R square plus omega L square available here can be replaced by Z square. So that K1 become Em omega L divided by Z square. Right. So after substituting Z impedance value, now we got this expression. Now we need to find K2 and K3. So consider the equation 1A. We'll consider the equation 1A. Em omega by L equal to K1 S square plus omega square plus K2S plus K3 into S plus RL. This is the equation 1A. Now we'll multiply inside this term. K2S into S, so K2S square. K2S into R by L. K2S into R by L. K3 into S. K3 R by L. Right. So this term is multiplied. Now we'll group the coefficient S square, S and constant. Em omega by L, S square. Take the S square common. Here s square term is available, k1. Here s square term k2 available. So k1 plus k2. Similarly, take s outside. Here s is available, k2 r by L. Here s is available plus k3. This k1 omega square k3 r by L is constant. So it is nothing but a quadratic equation like s square plus s plus coefficient. This is the coefficient of s square. This is coefficient of s. This is constant. Now we can equate the coefficient of s square on both the sides. Here coefficient of s square is k1 plus k2. Here s square is not available. So that is equal to 0. So k1 plus k2 equal to 0. That means k1 equal to minus k2. Right? So the k1 value we already know that. So k2 is nothing but minus of k1. Now we'll see the further simplification. Similarly, while equating the coefficient of s, coefficient of s is k2 r by L plus k3. That is equal to 0. That also 0. For here also s term is not available. So this term is become 0. From that we can find the k3 value. Right. Now we'll see k2, then we'll go for k3. So this is the coefficient of s is nothing but this term. This term is equal to 0. Now we'll see the further. So k2 equal to minus k1. K1 we already calculated, omega L Em by z square. So k2 equal to minus omega L Em by z square. Now we got the k2 value also. Now can k3. For that, on equating the coefficient of s. So we already discussed this k2 r by L plus k3 is the coefficient of s, that is equal to 0. That side no coefficient available. So k3 equal to minus k2 into r by L. Minus of k2 value already available. Here also one minus is there. Minus omega L Em divided by z square into r by L. So this negative, both negative become positive. This L got cancelled. So Em omega r divided by z square. Now we got the value of k1, k2 as well as k3. So that can be substituted in the equation, previous equation. Then we can go for the inverse Laplace. Now we'll refer the original equation. So this is the equation I of s, k1 divided by s plus r by L plus k2s plus k3 divided by s square plus omega square. Now substitute the value of k1, k2 and k3. k1 is omega L Em by z square into this term s plus r by L plus k2. k2 is minus, we know that k1 equal to minus k2. Minus omega L Em by z square into s plus k3. k3 is Em r omega by z square divided by this term s square plus omega square. Right. Now we split this term into two terms, two different terms. So omega L Em by z square. These are all constant. What we have, 1 divided by s plus r by L. So this is the standard form. Then only we can take the inverse Laplace, s by a, 1 divided by s plus a. Similarly here we can split this, minus omega L Em by z square. Here s is available, s divided by s square plus omega square plus Em r omega z square into 1 divided by s square plus omega square. Right. So now is brought into the standard form. This is constant. These are all constant. Here 1 divided by s plus rl. S divided by s square plus omega square. Here 1 divided by s square plus omega square. Right. Now we can easily take the inverse Laplace transform. Take inverse Laplace on both the sides. So inverse Laplace of I of s, that is nothing but I of t. Now again converted into t domain. Laplace inverse of 1 divided by s plus r by L. This is constant. And this is constant. Laplace inverse of s divided by s square plus omega square. This is constant. Laplace inverse of omega divided by s square plus omega square. So we are taking omega here, because then only we can go for sin omega t. Right. So Laplace transform of inverse of 1 divided by s plus ra. This is nothing but 1 divided by s plus a. That is nothing but e plus minus at. A is nothing but r by L. Right. 1 divided by s plus a is nothing but e power minus at. Here a is r by l. This is constant and this term constant. So s divided by s square omega square, s square plus omega square is cos omega t. This is a direct formula. Similarly, omega divided by s square plus omega square is sin omega t. Laplace inverse Laplace of omega plus omega divided by s square plus omega square is sin omega t. So now we taken all the formulas. This is nothing but 1 divided by s plus a is e power minus at. A is nothing but minus r by l. S by s square plus omega square is cos omega t. Omega divided by s square by omega square is sin omega t. Right. Now this term is constant. Em omega l divided by z square into e power minus r by l t. Not constant. This is a exponential function. Here cos omega t, sin omega t is available. Em r by z square is commonly available. So taken outside. So r sin omega t. Here r sin omega t is available. Em divided by z square is constant. Here Em divided by z square constant. Omega l is available. Minus and also minus omega l cos omega t. So this is the final expression, the transient current of the RL circuit while applying sine wave. Now we will go for further simplification in terms of impedance triangle. Now refer this triangle, right angle triangle with the resistance omega l. So this R is available. Horizontally we have RL and omega l. This is called the impedance triangle. This is angle between R and omega l. So this is the inductive reactance. So this is the impedance. The sum of these two is the impedance. Z equal to square root of R square plus omega l square. Resistance, inductive reactance, the sum of these two is the impedance. So from this triangle we can find the tan theta. Tan theta equal to opposite side by adjacent side. Omega l divided by R. From that tan pi is equal to tan inverse omega l by r, right? We can find the pi value, angle value. Similarly cos pi equal to adjacent side by hypotenuse, r divided by z. So from that cross multiply this, so r equal to z cos pi. Similarly sin pi equal to opposite side by hypotenuse, omega l divided by z. Cross multiply this, omega l equal to z sin pi. So in the transient previous equation we got the final expression I of t. In that z cos pi can be replaced with r. This r is replaced by z cos pi. Similarly omega l replaced by z sin pi. That's why we are calculating these two values, right? And also if need we can find the pi value also, angle between pi also calculated. So in this equation, previous equation, we are going to replace r with z cos pi, omega l with z sin pi. Right, now we'll see the further simplification. So this the previous equation, omega l em e power minus r by l t divided by z square plus em by z square is common. Sin omega t, right? So this into r. R is replaced by now z cos pi. Minus z sin pi into cos omega t. This omega l is, this is a omega l. This omega l is replaced by z sin pi, right? So this is r replaced by z cos pi. This is omega l replaced by z sin pi. Now it is coming under, now this z is commonly available. You can take outside. This is nothing but sin a cos b minus cos a sin b, right? Sin a cos b minus sin b cos a. So that is nothing but this format is available. So that can be written as sin a minus b. A is omega t, b is pi. So it becomes sin omega t minus pi, right? So for the simplification we substituted r value, omega l value, z is taken outside. So this is nothing but sin a cos b minus sin b cos a. That is nothing but sin a minus b. A is omega t, b is pi. So this is a transient term. This term is called transient term. This is the steady state term. So this is the final expression. In after substituting from the impedance triangle, we got one more equation that contain transient as well as steady state. So in this video we discuss the RL circuit with the sine wave. RL circuit with the DC circuit, DC source is available separate video. This is AC circuit. We are supplied EM sin omega t is applied. There we are applied DC voltage. So we discuss, initially we got the KVL by using KVL equation is framed, then Laplace inverse is taken. By using partial fraction techniques, we split the terms. After that inverse Laplace is taken. After simplification we got this equation. Again it is further simplified by impedance triangle. Finally we got the equation with steady state term and transient term. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the sinusoidal response of RC circuit. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we will see the topic sinusoidal response of RC circuit. So consider the RC circuit shown below. Let the circuit is excited by the sinusoidal source E of t equal to Em sin omega t when the switch is closed at t equal to 0. So this is the RC circuit. Resistor and capacitor is connected by the switch. The voltage applied is the sine wave, sinusoidal source E of t, that is equal to Em sin omega t. At t equal to 0, the switch is closed. We need to see the response of this RC circuit based on the sine wave Em sin omega t. Let I of t be the current through the circuit. Let us assume that there is no energy stored in the circuit. So before closing the switch, there is no energy stored, right? And also it is I of t is the current flowing through the circuit. Now we are going to apply the Kirchhoff's voltage law, KVL, to this circuit in order to frame the equation. Applying KVL for the given circuit when the switch is closed at t equal to 0. What is the Kirchhoff's voltage law? The voltage rise or applied voltage equal to voltage drop across resistor and capacitor. Otherwise voltage rise equal to voltage drop. So based on that, Em sin omega t, this is the voltage applied or voltage rise, that is equal to voltage drop across resistor R into I, voltage drop across the capacitor 1 by C integral I dt. So this is the KVL equation from the given circuit. The applied voltage is Em sin omega t. We need to take this equation number 1. Now we need to take the Laplace transformation on both the sides in order to convert the t domain into S domain. Again we will take the inverse Laplace. At that time we will get the transient current. So we will take the Laplace transform on both the sides. R is constant, I is converted as I of S. Then 1 by C integral I dt. Laplace transform of integral I dt is I of S divided by S. We need to subtract the initial condition, but we assume that initial condition is 0. Before closing the switch there is no energy stored. Then Em is constant, sin omega t. Laplace transform of sin omega t is omega divided by S square plus omega square. This is the formula. So take the I of S commonly. So R plus 1 by Cs equal to Em omega divided by S square plus omega square. Now bring this term in the denominator so that we can find the I of S equal to Em omega divided by S square plus omega square into 1 divided by R plus 1 by Cs. Now we'll go for the further simplification. We'll go for further simplification so that we can go inverse Laplace, right? So here the R, take the R outside. So it become 1 plus, here R is not available. So multiplied 1 divided by C into S into R. Now take this S outside, 1 by S. Take the 1 by S outside. But here S is not available. So it is multiplied by S plus 1 by RC. Our aim is to bring the standard form S plus A. A is nothing but 1 divided by RC. So that first we are taking R outside, then 1 by S outside. So that it is brought in the standard form S plus. Here already S square plus omega square is available. Similarly here also you brought to S plus A. Now If we go for the further simplification, it is nothing but Em omega, this S is available. S R by S will go to numerator, it become S by R. S square plus omega square into S plus 1 divided by RC. Now we need to take the inverse Laplace, but it should be converted into partial fraction. Then only we can take the inverse Laplace. Now we'll see the how to convert into partial fraction. So this I of s can be written as k1 divided by s plus 1 by RC plus k2 into s plus k3 divided by s square plus omega square. So there are 2-3 methods available. Based on that it is splitted, right? Here s square is available, so that we have k2s plus k3. Here only s is available, so only one term k1. So in this term we can easily take the inverse Laplace, s plus a. This is s square plus omega square, right? So that we are going for partial fraction. But we need to find the value of k1, k2 and k3. Take this equation number 2. Now we'll see how to find the k1 value, k2 and k3. So this is the equation available. We split it into 2 terms. Now we'll take this LCM. This term and these 2 terms will take commonly LCM. So that here s plus 1 by RC available. This term is not available. So it is multiplied. K1 into s square plus omega square plus k2s plus k3. This term is not available here. So multiplied. S plus 1 by RC. So these 2 terms available on both the sides got cancelled. S plus 1 by RC, s square plus omega square got cancelled. So what we have, omega Em s by R. Omega Em s by R equal to k1 into s square plus omega square plus k2s in plus k3 into s plus 1 by RC. Take this equation number 3. Now we need to find k1, k2 and k3. So by substituting, so if we substitute s equal to minus 1 by RC, this term becomes 0. Totally this term becomes 0. So we can easily calculate k1. So we need to identify the value so that any term becomes 0. Accordingly we need to submit. So here s plus 1 by RC is there. By substituting s equal to minus 1 by RC, this entire term 0. So we can find k1. Then k2 and k3 can be calculated by equating the coefficient of s square and s. So first we will put s equal to minus 1 by RC in order to find the k1. Now we will see how to find the k1. So omega Em by R into s. S is nothing but minus 1 by RC equal to k1 into s square. So minus become plus 1 divided by R square plus c square plus omega square into k2 into s. S is minus 1 by RC plus k3. S plus 1 by RC. S is minus 1 by RC. So this totally, this term become 0. Only this term is available. So here minus is there. Minus omega, the Em minus omega Em divided by R 2 times available. R square C equal to k1 into this term. 1 divided by R square plus C square plus omega square. Now we'll take this term commonly LCM. So 1 plus this term not available here, it is multiplied. R square, C square, omega square, right? So finally we got this value. Now our aim is to find this k1. So bring this term in the denominator, right? So we'll bring the term into denominator. What happened? Minus omega Em divided by R square C. This term will go to numerator, this term will go to denominator. So R square C square divided by 1 plus R square C square omega square, right? So this R square got cancelled. C one term got cancelled. So minus omega Em C divided by 1 plus R square C square omega square equal to k1. So now we got the value of k1, right? So now we are going to take this omega square C square outside for the further simplification. Take this omega square C square outside so that we can cancel. So here this term is not available, so it is divided. 1 divided by omega square C square plus R square. These 2 terms taken outside. So one term got cancelled, omega. Similarly C also one term got cancelled. So after the simplification, what we got? minus Em divided by omega c into r square plus omega square c square, that is equal to this k1. But this impedance for a frequency domain, the magnitude of the impedance of the RC circuit is given as Z square equal to R square plus 1 divided by omega square C square. That is, this term can be easily written as Z square. It's called a impedance. Right. Now we'll see how to find the K2 and K3. K2 and K3 we are going to compare the equating the coefficient. So first we will take the equation 3. This is the equation 3. Now we'll multiply this inside in order to bring the coefficient. So K1 into S square, K1 into omega square. Here K2 S into S, so that K2 S square, K2 S in divided by 1 by RC, K3 into S, K3 divided by 1 RC. Now we'll take the S square commonly. Here S square available K1. Here also S square available K2. Then S term commonly, right? Here S is available K2 divided by RC. Here S is available K3. K1 omega square is constant. K3 divided by RC also constant. Now it is in a quadratic form. S square, S and common term and constant. Now we can equate the coefficient on both the sides. Equating the coefficient of S square and S. First we will equate the S square. Here S square is K1 plus K2. But here S square is not available. So it is 0. That means K2 equal to minus K1. Minus of already K1 is minus Em by omega c Z square. So both become positive. It become Em divided by omega c Z square. Right? So this is the K2 value. Now we'll equate the coefficient of S. Coefficient of S is K2 divided by RC plus K3. That is equal to 0. Here K2 term is, S term is not available. Here S term is available here. Omega Em by R. Omega Em by R equal to K2 divided by RC plus K3. Right. So bring this K3, what we need is K3, bring this term that side. So minus, now we'll see the, bring this K2 divided by RC that side. So minus K2 by RC. Omega Em by R minus 1 by RC, substitute this K2 value. K2 is Em omega c Z square. Now multiply inside. Omega Em by R equal to Em divided by R into C square. C available 2 times into RC square omega Z square. Right. Now Em by R is commonly available. So that omega minus 1 divided by omega c square Z square. Em by R is taken outside. So if I now take this LCM. So that Em by R omega c square Z square. Here only omega is available. C square Z square not available. So it is multiplied. Omega c square Z square minus 1. Right. So already here no term is available. So all these 3 terms are multiplied. Already omega is there. So omega square c square Z square. So this is the value of K3. Now we can substitute here. R square plus 1 divided by omega square c square equal to Z square. We are going to substitute this Z square available. We are going to substitute the value impedance in the above equation for further simplification. Em by R omega square c square. The Z square is substituted as R square plus 1 divided by omega square c square divided by omega c square into Z square again. Minus 1 already there. R square plus 1 divided by omega square c square. Now we'll go for the further simplification. So here further simplification, Em by R omega square c square into R square plus 1 divided by omega square c square divided by omega c square Z square. Now we will multiply inside. This time we are multiplied inside omega square c square R square. Then omega square c square divided by omega square c square. Both the terms are equal, minus 1. Right. Divided by omega c square Z square. So Em by R This term got cancelled, become 1. Already here minus 1 is there, so both are cancelled. So omega square c square r square divided by omega c square z square, right? So here the z square is not substituted, only z square substituted here. Again this term is brought into z square, right? Earlier we substituted z square and numerator as well as denominator. Now denominator z square is kept as it is, right? So we'll see the further simplification. So here got cancelled, omega one term got cancelled, c square totally got cancelled, r one term got cancelled. So em omega r divided by z square. So this is the k3 value. Now we got the k3 value also. Now we'll consider the equation 2, then we'll substitute the all three constant k1, k2 and k3. So equation 2 is k1 divided by s plus 1 by rc plus k2s plus k3 divided by s square plus omega square. Now we'll substitute k1 minus em by omega c z square, k2 plus em by s omega c z square, k3 is omega r em divided by z square, what we calculated. Now we'll go for the further simplification. In order to take the inverse Laplace, the terms are rearranged. These are all constant. Minus em by omega c z square is constant into 1 divided by s plus 1 by rc. So here we can take the inverse Laplace. Similarly, em by s omega c square z square into 1 divided by s square omega square. Here these are all constant. 1 divided by s square omega square. Is further it is rearranged. Minus em divided by omega c z square into 1 divided by s plus 1 by rc. This is in the nothing but 1 divided by s plus a form. Em divided by omega c z square, s is multiplied here. S divided by s square plus omega square. So this is also one of the form available in the Laplace. Similarly here omega is written. Omega divided by s square plus omega square. Right. So this 1 divided by s plus 1 by rc is nothing but e power minus 1 by rc t. That is nothing but 1 divided by s plus a is e power minus at. A is nothing but 1 by rc. Similarly, s divided by s square plus omega square, while taking the inverse Laplace, it is cos omega t. Similarly, omega divided by s square plus omega square is sin omega t. Right? So that it is rearranged like that. Now we'll take the common terms outside. Em by z square is commonly available on both the terms, so that it is taken outside. So here r into sin omega t. Here 1 divided by omega c into cos omega t. Em by z square is taken outside. So this is finally the transient current of the RC circuit. Now we can go for simplification using the impedance triangle. So we'll go for further simplification of this transient current by using the impedance triangle. So this is an impedance triangle, resistance available. This is capacitive reactance. This is impedance. Z square equal to R square plus 1 divided by omega square C square. So from this we can find the tan theta. Tan theta is opposite side by adjacent side. 1 divided by omega C divided by R. So that pi equal to tan inverse 1 divided by omega C R. So if we want to find the pi value angle, we can find from this formula. Similarly, sin pi. Sin pi equal to opposite side by hypotenuse. 1 divided by omega c divided by z. So from that you multiply this term. So 1 divided by omega c is z sin theta. Cos theta is adjacent side by hypotenuse. R divided by z. Cross multiply this. So r equal to z cos pi. Right. So these two values we can substitute in the previous equation what we calculated. So this is the equation what frame. Here this r is there. So r is replaced by z cos pi. Here 1 by omega c is replaced by z sin pi. Now we'll refer the previous equation. Here this r is replaced by z cos pi. 1 divided by omega c is replaced by sin pi. So that we got one more simplified form. Now z available commonly, take the z outside. Already here z square is there. So one z got cancelled. So what we have, sin omega t cos pi plus sin pi cos omega t. This is nothing but sin a cos b plus sin b cos a. A is omega t, b is pi. That is nothing but sin a plus b. That is sin omega plus pi. So in order to bring this form only, we use the triangle. So z cancel, only em by z is available. This term is already available. There is no change in this term. So this is the transient. This term is refer the transient term. This term refer the steady state term. Right. So finally we got the transient current in terms of transient term and steady state. In this video we discuss the sinusoidal response of the RC circuit. First by applying KVL we frame the equation. Then we take the Laplace transform. After simplification we take the inverse Laplace. Then again it is substituted with the impedance triangle. Finally we got the transient current in terms of transient term and steady state term. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the sinusoidal response of RLC circuit. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we will go to the topic. Sinusoidal response of a RLC circuit. So let us consider the circuit RLC, resistor, inductor and capacitor connected in series, that is excited by the sinusoidal voltage, that is E of t equal to Em sin omega t. The switch is available, the switch is closed at t equal to 0. So this I of t is the transient current. We need to find the response of this transient current. So while applying the sine voltage, sinusoidal voltage, what is the response of RLC circuit, that we need to identify. Consider the RLC circuit shown in diagram excited by the sinusoidal source. E of t equal to Em sin omega t when the switch is closed at t equal to 0. Let I of t be the current through the circuit. Let us assume that there is no stored charge before closing the switch. Right. So this RLC series circuit, Em sin omega t is applied at t equal to 0. I of t is the current through the circuit. There is no charge in the circuit, that is there are two storage elements available, inductor and capacitor. So there is no charge before closing the switch. Now we are going to apply the Kirchhoff's voltage law for the given circuit. Kirchhoff's voltage law is nothing but the applied voltage is equal to Em sin omega is equal to voltage drop across resistor, inductor and capacitor. So that is given by KVL. Otherwise voltage rise equal to voltage drop. So the voltage drop across R is R into I of t. Inductor is L di by dt. Capacitor is 1 by C integral I dt. That is equal to applied voltage Em sin omega t. Right. So this is the KVL equation we got from this equation. Now we need to take the Laplace transform, then by inverse Laplace, so that we can find the I of t. While taking Laplace, this t domain converted into S domain. While taking inverse, again S domain converted into t domain, so that we can identify I of t. Now we will take the Laplace transform on both the sides. So this is a given circuit, is the given equation available. Take Laplace transform on both the sides. So R is constant, I of t, Laplace transform of I of t is I of s, plus L is constant, di by dt, Laplace transform of di by dt is s into I of s. Here initial charge will be there, but we assume that initial charge is 0. 1 by C is constant, integral I dt is I of s divided by s. Differentiation s into I of s, integral I of s divided by s. Em is constant, sin omega t. Laplace transform of sin omega t is omega divided by s square plus omega square. Now we taken the Laplace transform on both the sides. Take this I of s common, so that R plus L into S plus 1 by Cs, that is equal to omega em divided by s square plus omega square. Now bring this term in the denominator, that side. So I of s equal to omega em divided by s square plus omega square into 1 divided by r plus ls plus cs. Now we'll go for the further simplification. So we take the L and S outside, so that we can bring in the form S square into S, the standard form, quadratic form. So L is also taken, 1 by S is also taken. L divided by S is taken outside. So here both the terms are not available, so multiplied by S by L. Here L is available, so that L is taken outside, but S is not available. So S square, it becomes S square. Here L is not available, so multiplied by 1 by L, and S is available, so that is taken outside. So 1 divided by LC. If you multiply this inside, you will get the original term. So R into S by L plus S square plus 1 by LC. Right. So this, we can rewrite this L by S while going to in a numerator, it becomes S by L. Omega Em S by L divided by S square plus omega square into S square plus R by Ls plus 1 by Lc. So this is nothing but a quadratic equation. Ax square plus bx plus c. X is nothing but s. A is here 1. B is R by L. C is 1 by Lc. We will take this equation number 1. Right. The roots of this quadratic factor in the denominator may be real or complex. Hence, the following 3 cases are available. So now we will need to analyze this quadratic equation. So there are 3 cases. Roots are real and equal, real and different. Roots are complex conjugate. 3 cases are available. We will see the cases one by one. So the case 1 is the roots are real and equal. Both the roots are real and equal. So let us consider s square plus r by ls plus 1 by lc equal to s plus a the whole square. The root is a. Both are equal. S plus a into s plus a. Right? The 2 roots are available, that is real and also equal, where a is the root of the real root of the quadratic factor. So based on that, now by partial expression technique, the equation 1 can be expressed as I of s equal to omega em s by L divided by s square plus omega square, s square plus r by ls plus 1 by lc. So this can be written as s plus a square. This term is now we consider as s plus a the whole square. Right. Now that only the 2 terms now available in the denominator, s square plus omega square into s plus a the whole square. So by using the partial fraction technique, we can write this expression as k1 divided by s plus a, k2 divided by s plus a the whole square plus k3s plus k4 divided by s square plus omega square. While partial expression technique, 2 or 3 methods available. This is one of the method. Plus s plus a the whole square is there. So that we have 2 terms, k1 and k2. S plus a the whole square. Here s square is available. So here another 2 terms available. K3 into s plus k4. Right. So we need to take the inverse Laplace on both the side in order to get the I of t. Right. So while taking inverse Laplace, this k1 is constant. 1 divided by s plus a is e power minus at. The formula is there. 1 divided by s plus a is e power minus at. This k2 is constant. S plus a the whole square means t into e power minus at. When the power increases, here t also increases. Cube means t square. 4 means t cube. Like that it will increase. Plus im sin omega t plus or minus pi. The expression for it is directly written. We are not going for any solution. For this, the inverse Laplace is im sin omega t plus or minus pi. So this im is the maximum value of the steady state current. So this is the expression for transient current. For the case, roots are real and equal. K1 e power minus at plus K2t e power minus at plus im sin omega t plus or minus pi. Im is the maximum value. Now we'll see the second case. the roots are real and unequal. Two different roots. The two different roots are available. So s square, let us consider s square plus r by l s plus 1 by l c is equal to s plus a into s plus b. Earlier we have s plus a the whole square. Both the roots are a, but here different. S plus a, s plus b. One root is a, another root is b. So the roots are real and unequal, where a and b are the roots, real roots of the quadratic equation. Now the equation 1, by using the partial expression technique, the equation 1 can be expressed as omega em. This is equation 1. This equation 1 is now expressed as, so this term is expressed as s plus a into s plus b, right? So by partial differentiation technique, k1 divided by s plus a plus k2 divided by s plus b, right? Here s plus a, s plus b. Earlier s plus a the whole square is there, but here only two terms, s plus a, s plus b. And this is same as the previous, k3s plus k4 divided by s square plus omega square. Now we can take the inverse Laplace in order to find the transient current. So take inverse Laplace on both the sides, so that I of t equal to k1 is constant, 1 divided by s plus a is e power minus at, plus k2 is constant, 1 divided by s plus b is e power minus bt, plus im sin omega t plus or minus pi. This is very similar to the previous case. Im is the maximum value of steady state current, right? So here we have a1 k1 e power minus at plus k2 e power minus bt plus im sin omega t plus or minus pi. The second case, real and different. Now we'll go to the third case. The roots are complex conjugate, right? Earlier two cases are real, here now complex conjugate. When the roots are complex conjugate, the quadratic expression, quadratic factor can be rearranged as s square plus r by ls plus 1 by lc equal to, we can write in this like this, s square plus r by ls plus r divided by 2l the whole square plus 1 by lc minus r by 2l the whole square. So this is nothing but s plus a the whole square plus omega d square, right? So this is nothing but, so this s plus a is nothing but r by 2l. R by 2l is taken as a, so that s plus a the whole square, s square plus a square plus 2s into a, like that we can take. So this term is taken as omega d, right? Square root of 1 by lc minus r by 2l the whole square is taken as omega d. So it's a square root is there, so here will be omega d square, right? So a and omega d we are having two terms. Based on that, this expression is simplified as s plus a the whole square plus omega d square, right? Now we'll go for the, now by partial expression technique the equation one can be expressed, right? Now we'll see how to simplify the equation 1. So this is the equation 1. Now this quadratic equation is written as s plus a the whole square plus omega d square, based on the complex conjugate. So by partial differentiation we can split as k1s plus k2 divided by s plus a the whole square plus omega d square. I already told here square is there, right? So that we have k1s plus k2. This term is very similar to the previous, k3s plus k4 divided by s square plus omega square. So this term available in all three cases. This is the term based on the complex conjugate. Now by taking the inverse Laplace, we can get I of t equal to I naught e power minus at sin omega t plus theta. So the Laplace of this term is directly written. It's not having any simplification. This is very similar to previous case. Im sin omega t plus or minus pi. Im is the maximum value of steady current. This is the current, initial current. I naught is the initial current. So this is the expression for transient current when the roots are complex conjugate. So in this video we discussed the sinusoidal response of RLC circuit. We got by using KVL the equation is written. Then after taking the Laplace we got the equation 1. in the standard form. In order to solve, we have three different cases. We have quadratic equation. We have based on the three different cases. Roots are real and equal. Roots are real and different. Roots are complex conjugate. All three cases we simplified that by using partial fraction technique. Then by taking the inverse Laplace, we got the transient current I of 3 for all the three cases. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we will see the solved problem based on the sinusoidal response of RL circuit. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we will go to the topic. Sinusoidal response of RL circuit, solved problem 1. So this is the circuit given, RL circuit. Resistance 50 ohm, inductance 0.5 Henry. It is excited by the exponential function 100 e power minus 50 t. The switch T is available. I of T is the transient current. Now we will see the statement of the problem. In the series RL circuit shown in the diagram, the applied voltage is E equal to 100 e power minus 50 t. Find the first one, resulting current, initial rate of change of current. You need to find the two parameter. One is the current, resulting current, and initial rate of change of current. So when this first will apply in the time domain, the equation for the above is given. Based on the Kirchhoff's voltage law, the applied voltage E equal to resistive drop plus inductive drop. Voltage rise equal to voltage drop based on the KVL. So the voltage across the drop across resistor is R into I. Voltage drop across inductor is L di by dt, that is equal to E. So this is the equation based on time domain with the KVL. Now we'll apply the given values. We can substitute the given values. R equal to 50 ohm, L is 0.5 Henry, di by dt equal to applied voltage is 100 e power minus 50 t. Now in order to find the resulting current, first we will take the Laplace transform, so that T domain will be converted into S domain. After simplification, we have to take the inverse Laplace, so that again we'll get the current in the T domain. So we'll take the Laplace on both the sides. So 50 is constant. Laplace of I is I of S. 0.5 is constant. Laplace transform of di by dt is S into I of S. Right. Minus 0.5 I0 plus. This 0.5 is nothing but the initial current. Initial rate of change of current. That is equal to 100. 100 is constant. E power minus 50t is nothing but 1 divided by S plus A. Right, 1 divided by S plus A equal to e power minus 80. A is nothing but here 50. So 100 divided by S plus 50. Now Laplace is taken on both the sides. So I0 plus is the initial current through the inductor that we assumed as 0. Right, this is the initial current not mentioned in the problem. So that we will take this is equal to 0. So after this 0, what we got? 50 I of S plus 0.5 S into I of S equal to 100 divided by S plus 50. Right? So we know that e power minus 80 equal to 1 divided by S plus A. Based on that, it is the Laplace transform is taken. Here A is nothing but 50. So e power minus 80 is 1 divided by S plus A. S plus 50. Right. Now we'll go for the further simplification. So here we'll take the I of S common. So that 50 plus 0.5 S equal to 100 divided by S plus 50. Bring this term in the denominator. So that I of S equal to 100 divided by S plus 50 into 0.5 S plus 50. Right. So now what we need is the S plus form. Standard form is S plus. Here 0.5 is there, so we will take the 0.5 outside. So that S plus 50 divided by 0.5. Right. 50 divided by 0.5 is nothing but 50 divided by 1 by 2. That is, this 2 will go to the numerator, so it becomes 100. So finally what we got? I of S equal to 200. This 100 divided by 0.5 become 200. s plus point s plus 50 into s plus 100. 50 divided by 0.5 become 100. So we will take this equation 1. Now by using the partial fraction, we'll split the terms. Then only we can take the inverse Laplace. Now we'll see the how to take the partial fraction technique. I will take this equation number 1. So now by partial expression technique, the above equation can be expressed as I of s equal to k1 divided by s plus 50 plus k2 divided by s plus 100. So now this term is split. Now we can easily take the inverse Laplace of this expression. But we need to find the value of k1 and k2. The equation 1, 200 divided by s plus 50 into s plus 100. That is written like this. That's so that this equation 1 is equal to this partial fraction technique. K1 divided by s plus 50 plus K2 divided by s plus 100. Now we'll take the LCM. We'll take this LCM here. Here only one term available. So it is multiplied by s plus 100. This term is multiplied by s plus 50. So these two terms available on both the sides. So got cancelled. So finally what we have, 200 equal to k1 into s plus 100 plus k2 into s plus 50. Now we need to find the value of k1 and k2. We need to substitute the value of s such that we need to find here k1 and k2. First select s equal to minus 100. So if we put s equal to minus 100, what happened? This term become 0. So we can easily calculate k2. Similarly, s equal to minus 50. If we substitute here s equal to minus 50, this term becomes 0, so that we can easily calculate k1. So we need to decide the s value such that any one term got cancelled. So here 100 is there, so we are substituting minus 100. Here 50 is there, so we are substituting minus 50. Right. First we will put s equal to minus 100, so that 200 equal to k1 into minus 100 plus 100 plus k2 into minus 100 plus 50. So this term becomes 0. So 200 equal to 0 plus minus 50 into k2. That is 200 equal to minus 50 k2. So k2 equal to 200 divided by 50. Minus 200 by 50. So k2 equal to minus 4. Right. Similarly, we can go for s equal to 50 minus 50. So 200 equal to k1 into minus 50 plus 100 plus k2 minus 50 plus 50. So this term become 0. So 200 equal to 50 k1. So k1 equal to 200 by 50. K1 equal to 4. Right. So there k2 equal to minus 4. K1 equal to plus 4. Now we got the both the value k1 and k2. So that we can write the equation 1 as k1 divided by s plus 50 plus k2 divided by s plus 100 can be written as k1 equal to 4, k2 equal to minus 4. Right. Now we'll take the Laplace inverse, take inverse Laplace on both the sides. So we are using the same formula, e power minus at equal to 1 divided by s plus a. Right. Here minus mean here plus. So 4 is constant, 1 divided by s plus a is 50. So e power minus 50t. Minus 4 is constant, e power 1 divided by s plus a. This is 100. So e power minus 100t. Right. So this is a is 50 first term, second term a is 100. Based on that 4 e power minus 50t minus 4 e power minus 100t. Based on this expression, inverse Laplace. Now we calculated the current in resultant current of the circuit. Now we'll go to the second part. The rate of change of current, that can be done by di by dt. Initial rate of change of current means di by dt at t equal to 0. Initially the current is 0. So we have to differentiate the current equation for current with respect to t and substitute t equal to 0, so that we can find initial rate of change of current. Right. So d by dt of this expression for current, e power minus 50t minus 4 e power minus 100t, what we got in the first division. This is the expression for current I of t. Now we have to differentiate. 4 is constant, e power minus 50t is nothing but minus 50 into e power minus 50t, right? So the differentiation of e of x is nothing but x e power x. So this is the basic formula for differentiation of e of x, right? So this x will come in the front side. So minus 50 into e power minus 50 into t. So minus 4 is constant. Differentiation of e power minus 100t is minus 100 into e power minus 100t, right? So 4 into minus 50, minus 200 e power minus 50t. So here minus, here also minus is there. We don't plus 4 into 100, 400 e power minus 100t. So this is the differentiation of the current equation. Now we need to substitute t equal to 0. So that is the initial rate of current. Here for the t value we need to substitute 0. So minus 200 e power 0 plus 400 e power 0. We know that e power 0 is 1, value is 1. So minus 200 plus 400. So totally it is 200 ampere per second. So initial rate of change of current is 200 ampere per second. So in this video we discussed the solved problem based on the RC circuit excited by the exponential function, sinusoidal function or exponential function. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the solved problem based on the sinusoidal response of RL circuit. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. In the network given, find the transient current. So this is the RL circuit available. Resistor and inductor connected in series, 10 ohm and 0.1 Henry. It is excited by the sinusoidal waveform. 100 sin 10 sin 100t. So voltage source applied. This is the current, transient current I of t. We need to find the expression for this transient current. So in the time domain, the equation for the above circuit based on the Kirchhoff's voltage law, the applied voltage equal to resistive drop plus inductive drop. Voltage rise equal to voltage drop. So R into I plus L di by dt equal to E. Now we'll substitute the value here. So R is 10 ohm, 10I plus inductor is 0.1 di by dt. Applied voltage is 100 sin 10 sin 100t, right? Our aim is to find the transient current. So first we will find the Laplace. We'll take the Laplace transform on both the side so that the t domain will be converted into s domain. After simplification we need to take inverse Laplace so that again we'll get the t domain. So take Laplace transform on both the side. 10 is constant. The Laplace of I is I of s. 0.1 is constant. The Laplace of di by dt is s into I of s. That is equal to 10 sin 100t. Laplace of sin 100t is 100 divided by s square plus 100 square. That is nothing but this omega divided by, the formula is omega divided by s square plus omega square. Here omega value is 100. So 100 divided by s square plus 100 square. So take this I of s common. So 10 plus 0.1 s equal to is 10 into 100, 1000 divided by s square plus 100 square. Right. Now we'll bring this term in the denominator on that side. So that 1000 divided by s square plus 100 square into 0.1 s plus 10. Now we'll go for the further simplification. So we need in the form s plus, so that this 0.1 is taken outside. Then only we'll get s plus. So 0.1 is taken outside, s plus 10 divided by 0.1. This 0.1 not available here. So 10 divided by 0.1 is 100. So we'll take this equation number 1. 10,000, right? This 0.1. 1000 divided by 0.1 become 10,000. Divided by s square plus 100 square into s plus 100. Right. Now we need to take the inverse Laplace, but we need to convert into standard form. Then only we can take the inverse Laplace. So this term is written as partial expression technique. The above expression can be written as A divided by S plus 100 plus Bs plus C divided by S square plus 100 square. Right, here only S is there, so only one constant A. Here S square is there, so two constant Bs plus C. So this equation 1, by using partial expression technique, it is written like that. This one can be, we can easily take the inverse Laplace, but we need to find the value of A, B and C. Now we'll go for the further simplification. So this is equation 1 that is written in the partial fraction technique. So both are same. Now we'll take the LCM on both sides. We'll taking LCM on both sides. This term is multiplied with A. This term is multiplied with Bs plus C, because here only one term is available. So A into S square plus 100 square multiplied. A plus Bs plus C into S plus 100. Now these two terms available on both the sides, so it is cancelled. So 10,000 equal to A of S square plus 100 square plus Bs plus C into S plus 100. I will take this equation number 2. So the next aim is we need to find the value of A, B and C. So we need to substitute the S value such that any one term got cancelled, so that we are able to find the remaining terms. So if you put S equal to minus 100, what happened? This term become 0. So we need to decide the S value such that it will equate to 0. If you put S equal to minus 100, this term is 0. Now we'll see what happen if you substitute S equal to 100, minus 100. So 10,000 equal to A of minus 100 square. S square is minus, S is minus 100 plus 100 square plus Bs plus C into minus 100 plus 100. So this is nothing but Bs plus C, right? Not only B, Bs plus C. So the total term is 0. This term is 0. So here also it is 0. So only here minus 100 square is 10,000. Already here 100 square 10,000. So totally 20,000. 10,000 equal to 20,000 A. So A equal to 10,000 by 20,000, it is 0.5. So now we calculated the value of 0.5. So B and C we can calculate by equating the coefficient. Equating the coefficient on both the sides. Now we'll consider this equation 2. We'll simplify this equation and then we can equate the coefficient of S and S square. So this is the equation 2. 10,000 equal to A S square plus 100 square plus Bs plus C into S plus 100. You multiply inside. 10,000 equal to A S square plus A into 100 square. Similarly here Bs into S, so Bs square. Bs into 100, so 100 Bs. C into S, C into 100. So now we'll take the S square coefficient, S square outside. So here S square is there, A. Here S square is B, so A plus B. Take S outside. Here S is there, so 100B. Here one S is there, C. Right? The S is taken outside, so 100B plus C. This 100 square is 10,000. 10,000 A. Plus here 100 is there, 100C. These two are constant. So this is coefficient of S square, A plus B. This is coefficient of S, 100B plus C. This is constant. Now we equate the coefficient of S square. S square is A plus B. Here S square term is not available. So A plus B is 0. So that B equal to minus A. A already we calculated 0.5. So B equal to minus 0.5. Similarly equating the coefficient of S. 100B plus C. So here S coefficient is not available. So 100B plus C equal to 0. So C equal to minus 100B. So minus 100 into B is nothing but minus 0.5. So minus 100 into minus 0.5 is 50. So now we calculate the value of A, B as well as C. A is 0.5, B is minus 0.5, C is 50. Now we'll go for the further simplification. So this is the equation 1. In that A value substituted 0.5, B value is minus 0.5, C value is 50. Now we'll split the term. Here two terms will split it. So minus 0.5 s divided by s square plus 100 square. 50 divided by s square plus 100 square. See now three terms available. This is rewritten. 0.5 divided by s plus 100 minus 0.5 s divided by s square plus 100 square plus 50 divided by s square plus 100 square. Here multiplied by 100 and divided by 100 in order to bring the standard form. So that what is available here, after multiplying 100, so 0.5 divided by s plus 100, same thing. Here it is rewritten like this. 50 divided by 100 is written. 100 divided by s square plus 100 square. So that we can take the inverse Laplace easily. Right. Now, so only thing we have multiplied and divided by 100 and rearranged. So the Laplace, inverse Laplace of this 0.5 is constant. 1 divided by s plus a is nothing but e power minus at. Based on that, e power minus 100t. This a is 100. Right. So it is based on e power minus at equal to 1 divided by s plus a. A is 100. This s divided by s square plus 100 square is cos 100t. Here omega is 100 cos omega. Similarly 100 divided by s square plus 100 square is sin 100t. These two are direct formulas. That is s divided by s square plus omega square is cos omega t. Omega divided by s square plus omega is sin omega t. Here omega is 100. Now this 0.5 is available commonly taken outside. E power minus 100t minus cos 100t plus sin 100t. So this is the expression for current, transient current. So in this video we discussed the solved problem based on the RL circuits, RL series circuit excited by sinusoidal wave. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers, in this video we will see the solved problem based on the sinusoidal response of RC circuit. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. Transient sinusoidal response of RC circuit, solved problem 1. So this is a given circuit. R and C is connected in series. R value 10 ohm, C value 60 farad. This is the transient current. For the given network, find the transient current. The question is we need to find the transient current. The voltage is sinusoidal voltage, 20 sin 50t. So applied voltage. So in this time domain, the equation of the above circuit is given as by using the KVL, Kirchhoff's voltage law. Applied voltage equal to voltage drop across resistor and capacitor. That is the Kirchhoff's voltage law. Voltage rise equal to voltage drop otherwise. So 20 sin 50t equal to resistive drop plus capacitive drop. Resistive drop is R into I. R value is 10I. The capacitance drop is 1 divided by 60. The C value 1 by C integral I dt. So by using KVL we obtain the equation for the given circuit. Our aim is to find the I of t. So we need to take the Laplace transformation on both the sides in order to convert t domain into s domain. After simplification we need to take inverse Laplace so that we will get the transient current. Take Laplace transform on both the sides. So 10 is constant. Laplace transform of I is I of s. 1 divided by 60. Integral I dt. Laplace transform of integral I dt is I of s divided by s. Equal to this 20 is constant. Laplace transform of sin 50t is 50 divided by s square plus 50 square. That is nothing but omega divided by s square plus omega square. Omega value is here 50. Now we'll take the I of s common. So 10 plus 1 divided by 60s equal to 20 into 50 is 1000 divided by s square plus 50 square. Now we'll take this 60 LCM. So the 60 is multiplied here. 10 into 60s plus 1 divided by 60s equal to 1000 divided by s square plus 50 square. I will go for the further simplification. So this is nothing but I of s into 10 into 60 is 600. 600s plus 1 into 60s. That is equal to 1000 divided by s square plus 50 square. Now we'll bring this term in that side. So this 60s will go in the numerator. 600s plus 1 will go to the denominator. So 1000 divided by s square plus 50 square into 60s divided by 600s plus 1. Now we'll go for the simplification. This 60 and 600 goes 10 times, is 6 times, right? So this again, this 600 and 1000 goes 6 times, this goes 10 times, 6 goes 10 times in 60. So 10 into 10, 100 yes, right? So finally we got, so first we will divide 1000 divided by 600. So 10 times, this is 6 times. This 6 is divided by this 60. So 10 times. 10 into 10, 100 s divided by s square plus 50 square into s plus 1 divided by 600 is 0.0016. Now we'll take this equation number 1. Now we need to go for the inverse Laplace, but we cannot take the inverse Laplace of this form. So we need to go partial fraction technique. After partial fraction, we can take the inverse Laplace. Now we'll see how to take the partial fraction technique. So now by partial expression technique, the above equation can be expressed as, we can split the term. That is the main aim of the partial expression. So that we can easily take the inverse Laplace. A divided by s plus 0.006. This is one term, 0.0016 plus bs plus c divided by s square plus 50 square. In partial expression technique, 2 or 3 methods available. This is one of the method. Here s is available, so only one constant a. Here s square is available, so that bs plus c, 2 constants are available. So this is the equation 1. That is written now like this. So both are equal. So equation 1, this is based on the partial fraction. Now we'll take the LCM of these two terms. So this term is multiplied with a, this term is multiplied with bs plus c, because here only one term available, this term not available, so it is multiplied. Now these two terms available on both the side go, so got cancelled. So finally what we got, 100 is s equal to a s square plus 50 square plus bs plus c s plus 0.0016. Now we'll take this equation number 2. So next our aim is to find the value of this a, b and c. A, b and c. So that we can go for partial inverse Laplace. Now we'll substitute the value of s such a way that it should cancel any term, so that we can find the other term. For example, here 0.0016 available. If we substitute s equal to minus 0.0016, this term become 0. So that we can easily calculate the value of a. So that is our a. So choose the s value such that the term got cancelled. So substitute s equal to 0.0016. So 100 into s is minus 0.0016 equal to a into s square minus 0.0016 square plus 50 square plus b into s minus 0.001s plus c into s plus 0.0016. S is minus 0.0016, right, 0.00. So these two terms are got cancelled, it become 0. So this 100 into this value is minus 0.16 equal to a, the square of this value, and it is added. Finally we got this 0.016 is this much value. So a equal to minus 0.16 divided by 2500.0000256. So by simplifying, what we got, minus 0.0000639. Right? Now we calculated the value of the a. B and C can be calculated by equating the coefficient of the equation without substituting the value, by using coefficient. So this is the equation, simplified equation, right? A S square plus that equation 2 is multiplied inside. So multiply after multiplication, after expanding the equation, we got this. Now S square, take S square outside. So here A is available, here B is available. So A plus B. Take S outside. Here S is available. So 0.0016 B. Here one S is available, C. This A 5 square, that is 2500 A. 0.0016 C. These two are constant. So this is coefficient of S square, coefficient of S, and constant. So this equation is nothing but from equation 2 after expanding we got this. That is simple. Either equation 2 is available, that is expanded. Now equating the coefficient of S square. Equation of coefficient of S square is A plus B. Here coefficient not available, 0. So A plus B equal to 0, so that B equal to minus A. Minus of minus, A value is minus, already minus is there. Minus 0.00639. So both the minus become plus. So B is 0.000639 plus. Right. Now we'll equate the coefficient of the S. S is 0.0016 B plus C. That is equal to here 100. Coefficient of S is 100. Right. So we'll go for further simplification. So C equal to 100. Bring this term that side. Minus. So it become minus 0.0016 into B. B value is this value. So after simplification we got 99.99. The C value is 99.99. Now we can substitute this value A, B, C in equation 1. Then we can go for inverse Laplace transform. So this is the equation after the partial fraction technique. A by this term and Bs plus C divided by this term. Now we got the value of A, B and C, so that we can substitute the value. A is minus 0.000639. B is plus 0.000639. C is 99.99. Right. So now we can split these two terms. Here only one term available, so it is splitted. Then only we can take the inverse Laplace. Right. So after splitting, what happened? So this term 1, term 2. Term 3 multiplied by 50 and divided by 50 in order to bring the standard form. So it is rewritten. All three terms are rearranged like that. So first we splitted, then we multiplied by 50 divided by 50. So this 0.000639 minus is constant. We'll write 1 divided by S plus 0.0016. This is one standard form. 1 divided by S plus A. So that we wrote like this. And this is constant. Then S divided by S square plus 50 square. This is one more standard form. S divided by S square plus omega square. Omega is here 50. Right. See here now it is written 99.99 divided by 50 is written separately. 50 divided by S square plus 50 square is written separately. Rearranged. Why it is written like that? Omega divided by S square plus omega square. That is another standard form. Right. Now this is constant written as it is. So 1 divided by S plus this value is nothing but e power minus AT. A is 0.0016. Right. 1 divided by S plus A. Inverse Laplace is e power minus AT. This constant is written like that. So S divided by S square plus 50 square is constant 50t. Cos 50t. Right. 50 is omega. Similarly 50 divided by S square plus 50 square is sin 50t. Right. These two are standard form. S square plus S divided by S square plus omega square is nothing but cos omega t. Omega is 50. Omega divided by S square plus omega square is sin omega t. Omega is 50. So this is the final transient expression for final transient current. Right. So this is nothing but I of t. Now it is converted into I of t. So in this video we discuss RC circuit excited by the sinusoidal waveform. Finally we got the transient current of the given circuit. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the solved problem based on the sinusoidal response of RC circuit. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic, sinusoidal response of RC circuit. Resistor and capacitor is connected in series. In that we need to find the transient current. So this is the circuit given. Resistance 5 ohm, capacitance 0.5 Henry connected in series. It's connected with the switch S. The applied voltage is exponential 5 e power minus t. So this is the transient current I of t flowing through the circuit. Now we'll see the statement of the problem. An exponential voltage V of t equal to 5 e power minus t is applied at the time t equal to 0 to a series RC circuit comprising R equal to 5 ohm, C equal to 0.1 farad. So 5 e power minus t voltage is applied at t equal to 0 to the RC circuit. Obtain the complete particular solution for current I of t through the capacitor. Assume zero charge across capacitor before application of driving voltage. So we need to find the transient current across the capacitor. There is no charge available before closing the switch, zero charge. So that is the condition given. So based on that, we'll go to that. Now first we need to frame the equation for the given circuit by using the Kirchhoff's voltage law. In time domain, the equation of the circuit is given as using the Kirchhoff's voltage law. Applied voltage equal to voltage drop across resistor and capacitor. Otherwise, voltage rise equal to voltage drop. So based on KVL, so this is applied voltage V of t equal to R into I, voltage drop across resistor, 1 by C integral minus infinite to 0 I dt. This is the initial charge available across the capacitor, minus infinite to 0. The switch is closed at 0, so 0 to t, 1 by C 0 to t I dt. So this is the voltage drop across the capacitor after closing the switch. So that is equal to V of t. Now substitute all the value. R is 5. So 5I plus initial charge is 0 given in the problem. C is 0.1, 0 to t I dt equal to 5 e power minus t. Right? So the applied voltage is exponential 5 e power minus t. So that 5I plus 1 divided by 0.1, 0 to integral 0 to t I dt equal to 5 e power minus t. So our aim is to find the transient current. So first we will take the Laplace transform of this equation so that t domain will be converted into S domain. After simplification we need to take again inverse Laplace so that we will get the transient current of the given circuit. So take Laplace transform on both the sides. So 5 is constant, Laplace of I is I of s plus 0.1 is there. Integral 0 to t I dt. The Laplace of this integral is I of s divided by s. That is equal to 5 is constant, e power minus t. Integral, the Laplace of e power minus t is 1 divided by s plus 1. That is e power, that is based on e power at equal to 1 divided by s minus a. Right? S minus a. Here s plus. Here minus. Right? So e power minus at equal to 1 divided by s plus a. A is nothing but here 1. So here e power t is equal to s 1 divided by s plus 1 based on this formula. Now we'll take I of s common. So I plus 5 plus 1 divided by 0.1 s equal to 5 divided by s plus 1. So this 1 divided by 0.1 is written as 10 divided by s. Right. Now we'll go for the LCM. We will take the LCM here. So here it is multiplied by 5s. So 5s plus 10 divided by s. Now we'll bring this term in the denominator of the other side. So that we'll get the expression for I of s. So that I of s equal to 5 divided by s plus 1 into s divided by 5s plus 10. In order to bring this, we can take this 5 outside. We have to bring the form s plus. The standard form is s plus. Here already available s plus 1. So 5 is taken outside. So s plus 2. The 5 goes 2 times. This 5 got cancelled. So s divided by s plus 1 into s plus 2. So equation 1. We will take this equation 1. In order to take the inverse Laplace, this would be converted into partial expression technique. We have to split the terms so that we can take the inverse Laplace transform. So by partial expression technique, the above equation can be written as k1 divided by s plus 1 plus k2 divided by s plus 2. So by using the partial expression technique, it is splitted. This expression can be easily, we can take the inverse Laplace, but we need to find the value of k1 and k2. Right. So this equation is now written like this. So both are equal. S divided by s plus 1 into s plus 2 equal to k1 divided by s plus 1 plus k2 divided by s plus 2. Now we'll go for the further simplification. Now we'll take the LCM, this s plus 1 into s plus 2. Here only s plus 1 is available, so multiplied by s plus 2. Here s plus 2 is available, so multiplied by s plus 1. So these two terms available on both the sides got cancelled. So s equal to k1 into s plus 2 plus k2 into s plus 1. Right. Now the next step is we need to find the value of k1 and k2. We have to select the s value such that the term got cancelled. For example, s equal to minus 2 means this term got cancelled, so that we can find k2. If s equal to minus 1 means this k2 got cancelled, we can able to find k1. So select the s value such that it will cancel any one term. So based on that, s equal to minus 2. We have to substitute s equal to minus 2. So s is minus 2 equal to k1 minus 2 plus 2 plus k2 into minus 2 plus 1. So this term is 0. So minus 2 equal to minus 2 plus 1 is minus 1 minus k2. So k2 equal to 2. Now we calculated the value of k2. Now substitute s equal to minus 1. Minus 1 equal to k1 minus 1 plus 2, k2 minus 1 plus 1. Thus this term is 0. So minus 1 equal to k1, so k1 equal to minus 1. Right. So select the value such that it will cancel any one term. Now we calculated k1 and k2. Now we can substitute this value. So this is equation 1. In this we are going to substitute the value of k1 and k2. So k1 is minus 1, k2 is 2. So minus 1 divided by s plus 1, 2 divided by s plus 2. Now we'll take the inverse Laplace on both the sides. Right. So minus 1 is constant. 1 divided by s plus a is nothing but e power minus t. 2 is constant. 1 divided by s plus 2 is e power minus 2t. The formula is 1 divided by s plus a equal to e power minus at. Here plus mean minus. Right. So first case a is 1. So that e power minus t. Second case a is 2. So that e power minus 2t. So here minus 1 into e power minus t plus 2 into e power minus 2t. We can rearrange. 2 e power minus 2t minus e power t, e power minus t. So this is the final expression for transient current. So current flowing through the circuit. So in this video we discussed the solved problem based on the RC circuit, resistor and capacitor. We obtained the transient current, expression for transient current. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the solved problem based on the sinusoidal response of RLC circuit. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. RLC circuit. R, L and C are connected in series. R value is 5 ohm, L is 1 Henry, C is 0.25 Farad. This is the transient current. We need to find the value expression for this transient current. The applied voltage is exponential form, 6 e power minus 2t. The switch is closed at t equal to 0. I will see the statement. In the circuit zone, the switch is closed at t equal to 0. Obtain I of t, transient current. Assume 0 current through the inductor L and 0 charge across capacitor before closing the switch. So before closing the switch there is no charge and no current in the inductor and capacitor. That is the initial value is 0. Now we'll see the equation for this given RLC circuit. In time domain, the equation of the above circuit is based on the KVL, Kirchhoff's voltage law. We can write the equation. So based on KVL is nothing but the voltage, applied voltage equal to voltage drop across resistor, voltage drop across inductor and capacitor. Otherwise, voltage rise equal to voltage drop across these three elements. So based on that, 5 into I, voltage drop across resistor, 5 into I, plus voltage drop across the inductor, 1 L di by dt, the L value is 1, and 1 by C integral I dt, that is the voltage drop across capacitor, 1 divided by 0.25 integral minus infinite to 0 I dt plus 1 divided by 0.25 0 to t I dt, that is equal to 6 e power minus 2t. So this is the applied voltage, right? So 5i is di by dt plus, so this initial value of charge is 0 even in the problem itself. This is the initial value of charge. This is the charge voltage drop across at the time t equal to 0. So this term becomes 0. So 5i plus di by dt plus 1 divided by 0.25 integral 0 to t I dt equal to 6 e power minus 2t. Now we need to take the Laplace transform in order to convert from t domain into s domain. After simplification, we have to take inverse Laplace so that we'll get the current in t form, that is a transient current. Now we'll take the Laplace transform on both the sides. So 5 is constant, Laplace of I is I of s. Laplace of di by dt is s into I of s. 0.25 is constant. The Laplace of integral is I of s divided by s. Differentiation means s into I of s, integral I of s divided by s, equal to 6. 6 is constant. E power minus 2t is 1 divided by s plus 2. So this is based on the formula e power minus at equal to 1 divided by s plus a, right? So a value is 2 here. So 1 divided by s plus a, s plus 2, based on this formula. I will take this I of s common. So 5 plus s plus 4 by s. 1 divided by 0.25 can be written as 4. 4 by s equal to 6 divided by s plus 2. Now I will take this LCM. So here s value not available, multiplied by s. Here also s not available, multiplied by s, it becomes s square plus 4 divided by s. Now we'll bring this term on that side, so that this term will go to the numerator, this term will go to the denominator, in order to obtain the expression for I of s. So it is written as s divided by s square plus 5s plus 4, these two terms available. So 6 divided by s plus 2. So this can be written as, this quadratic equation can be written as s plus 1 plus s plus 4, right? We know that if we add these two, will give the coefficient of s. If we multiply these two, it will give the coefficient of constant. So that is based on that it is splitted. It is a very simple quadratic equation, so it is splitted. If it is not there, we have to use the formula minus b plus or minus square root of b square minus 4ac divided by 2a. But here it is easily splitted. So finally we got I of s equal to 6s divided by s plus 2, s plus 1, s plus 4. So we'll take this equation number 1. Now we'll use the partial fraction technique in order to split this term. After splitting only we can take the inverse Laplace. Now we'll see how to take the partial fraction technique. So by partial expression technique, the equation is written as k1 divided by s plus 1 plus k2 divided by s plus 2 plus k3 divided by s plus 4. So if we split like this, we can easily take the inverse Laplace. So this equation, this is the equation 1, that is written like this. So both are same. Now we'll take these three term common, LCM. We'll take these three term LCM, so that for the further simplification. Here s plus 1 is available, so multiplied by s plus 2 and s plus 4. Here s plus 2 is available, so multiplied by s plus 1, s plus 4. Here s plus 4 is available multiplied by s plus 1, s plus 2. Now these 3 terms available on both the sides. So it is got cancelled. So finally we got this expression 6s equal to, right. Now we can we need to find the value of k1, k2 and k3. That is the next procedure. How to find the value of k1, k2 and k3? We have to substitute the value. Yes, we have to select the value of s such that it will cancel the 2 terms. Here 3 terms available. If we substitute s equal to minus 1, what happened? This minus 1 plus 1, 0. This term total is 0. Here also minus 1 plus 1, so total is 0. We can easily calculate k1. Similarly, if we substitute s equal to minus 2, this term and this term got cancelled. We can easily find k2. If we substitute s equal to minus 4, this k1 and k2 cancel. We can find k3. So select the s value such that it will cancel the terms. So s plus 2 is there. So we will substitute minus 2. Here minus 4. Here minus 1. We can select the value. So put s equal to minus 1. The minus 1 is substituted. See this plus 1 minus 1 becomes 0. Here plus 1 minus 1. That also becomes 0. Only this term is available. k1 into minus 1 plus 2 is 1. Minus 1 plus 4, 3. So it is 3. Minus 6 equal to 3k1. So k1 equal to minus 6 by 3 equal to minus 2. So now we got the value minus 2. Now substitute s equal to minus 2. So that we are able to find the next value. So s equal to minus 2 is substituted here. See here minus 2 plus 2 cancel. 0. It becomes 0. Here also minus 2 plus 2. This term becomes 0. Only k2 is available. k2 minus 1 plus minus 2 plus 1 means minus 1. Minus 1 plus 4 means 2. Right. So minus 12 equal to minus 2 k2. So k2 equal to minus 12 by minus 2. So 2 negative available 2 times. So it is cancel. Negative cancel. k2 equal to 6. Now we calculated the k2 value. Now we will substitute the s equal to minus 4. So this s value is selected from the equation itself. We have s plus 1, s plus 2, s plus 4. So first we substituted s equal to minus 1, then s equal to minus 2, now s equal to minus 4. Right, s equal to minus 4 substituted. See this here, plus 4 minus 4, 0. Here also minus 4 plus 4, 0. Only this term is available. k3 into minus 4 plus 1 means minus 3. Minus 4 plus 2 means minus 2. Right. So minus 24 equal to 6 k3. So k3 equal to minus 24 by 6. It is minus 4. Now we'll substitute the values. So this is the equation 1. By partial fraction technique we split it. Now we can substitute k1, k2, k3 value. k1 is minus 2. k2 is 6. k3 is minus 4. Now it is rearranged. Minus 2 into 1 divided by s plus 1 plus 6 into 1 divided by s plus 2 minus 4 into 1 divided by s plus 4. So it is written in a standard form. Right. We know that this e power minus at equal to 1 divided by s plus a. Right. So we will take the inverse Laplace on both the sides. By using the formula we can write. So minus 2 is written. 1 divided by s plus 1 is e power minus t. Here a is 1, s plus 1. So a is 1. So e power minus t. Similarly s plus 2. A is 2 here. So e power minus 2t. S plus 4. Here a is 4. E power minus 4t. Right. So based on this formula it is written. So finally we got the equation for transient current of the RLC circuit. Minus 2 e power minus t plus 6 e power minus 2t minus 4 e power minus 4t. Based on this formula written. So in this video we discussed the RLC circuit, sinusoidal excitation of the series RLC circuit. We obtained the transient current, expression for transient current. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening.